The issue of momentum disturbance in fluids is slightly different than diffusion in concentrations. So if you have a momentum flux like this, and if you have a zero velocity everywhere in the domain, it means that this is the direction of the velocity gradient. And because of this gradient in velocity, velocity wants to diffuse towards that gradient. So this is the pink curve shows the direction of the diffusion of velocity. If the viscosity is very high, then the diffusion time, if this is very high, then the diffusion time will be very low. So in order for this disturbance to propagate over a distance L, it would take a very short time. But if the fluid is very less viscous, if the fluid is less viscous, then the time of diffusion will be quite high. So after a certain time, you will see that the momentum has only diffused over to this distance. Effectively, if you take a cup of water, if you have a small tracer particle over here, it can be a pepper flake. You insert a small chopstick or rod or whatever you have, not rod but a small stick or a broomstick, and you move it. You will see that for the moving broomstick or a moving chopstick, if the distance is L, this pepper flake would start moving after a time L square upon nu. Actually, it is better to do this experiment in a large plastic container so that the walls do not create an additional flow. Okay, so do this experiment in a large container. Large meaning the container dimension should be much larger than this distance. So this is the container, this is the broomstick, this is the particle. So if you move this in this direction, you will see that after a while this pepper flake will start to move. But if you pour everything with honey and if you repeat the same thing, you will see that the moment you start moving the stick, the pepper flake also starts to move immediately. So for honey, the time taken for diffusion, so if I call it T diff H, it will be L square by nu honey, and time taken for momentum to diffuse in water, if I call it T diff W, it will be L square by nu W. So the time for honey divided by time for water will be nu water upon nu honey. And the kinematic viscosity of honey is quite large. So the time taken for the disturbance to propagate in honey will be quite small compared to the time taken for disturbance to propagate in water. You might have experienced this also when you are standing on a platform. So this is a very crudely drawn platform and this is you, a very crude version of you. When a train goes by very quickly on the tracks, depending on how far you're standing from the platform, and of course it is recommended, strongly suggested that you stand sufficiently away from the track. If you're sitting at a bench quite far away, okay, if you're sitting on this crudely drawn bench, then you probably won't be able to feel the effect of the disturbance of air because of the fast moving train until the train actually passes into a long distance. If you're sitting over here, maybe it will take 10 seconds for you to feel the effect of that gust of wind. But if you're standing close, you will feel it immediately. Okay, so if I draw a top view of this moving train is like a momentum disturbance, and after a time 2 seconds, this disturbance has reached only the first person, and after a sufficiently long time, the disturbance has reached the person sitting on the bench. Okay, so this is the meaning of it all.